Okay, so going back to gradient descent and looking at it as an algorithm, we may notice that we process the entire data set on every iteration. In order to estimate a parameter, we use the old value of that parameter and we modify it by the error estimate computed on the entire training data set. Okay, use that to estimate the gradient. So and this is infeasible for large data sets of the variety that we will encounter fairly frequently in a data science context. Okay. So a variation on gradient descent is what is called stochastic gradient descent. And stochastic, as usual, means probabilistic, means you're going to be selecting something at random. And so in this case, we select a single data point from the training set and use that to estimate the gradient as opposed to the entire data set. All right. And so we just continue on in that iteration as if that one data point was our entire training data set. And then on the next iteration, we select another point at random, and so on. Okay, so what you'll be doing here is your estimate of the direction of the gradient won't be as good because you're only considering one data point, but you'll be able to compute that iteration much faster, and so you'll get through more of them hopefully. And so a compromise between these two extremes, using the entire data set and using just a single value, is what some call mini-batch gradient descent, where at each step you pick a small subset of points as opposed to just a single pointer, as opposed to using the entire data set, and then you continue on as if that subset was your training data set. And so I think all three of these methods, when you look at this algorithmically, are really pretty simple, intuitive variations of each other. Now, they do have some different properties mathematically and statistically, which is why there's been a ton of work on them. But just from a programming perspective, they're pretty minor variants of each other, and they arise in a fairly natural way, just in the interest of almost a performance optimization. Okay. And I'll come back to that point in a moment. But first, let's look at what this kind of an effect this change has on the procedure. So here's an example of where I modified this gradient descent program that produced these plots to use stochastic gradient descent, where I just picked a single value. You can see it kind of, as it walks down the gradient, it kind of wanders about a bit more and doesn't always find the exact correct direction. And so it might take more iterations to get there. And also the error is kind of jumping around at each point. Now, I wouldn't read too much into this particular example. And if you run this a bunch of different times, you'll see a bunch of different patterns. Some of them will converge in just a few steps, and some of them will take a lot longer, and so on. But it does give you a flavor of the kind of cost to using this method, where it doesn't sort of make a beeline for the optimum point, like it did with gradient descent, where we used the entire training data. Okay. And an example using mini batches, this one happened to have sort of a little bit better of an error character, but you can still just see some noise here, and this one happened to take many more iterations to get to the middle. Okay. One other factor here is that as you're changing the method, stochastic, mini batches, changing the size of the mini batch, and so on, the learning rate may have an effect here too, right? So here the learning rate is pretty small, and so it looks like we're taking very small steps on each iteration. And if it gets too big, it might sort of jump down here to the bottom and then just bounce around for a while, hopping over the medium and not converging. Okay. And so the choice of method with the learning rate is sort of sensitive here, and in some cases for an application you may be doing a little bit of trial and error, and a lot of the research work goes into try to understanding these trade-offs more analytically. All right. So fine. So if that's two different methods for optimizing this optimization procedure, for applying performance optimization to this optimization procedure to handle larger data sets. But we made the point several weeks ago about scalability nowadays is really not about making things a little bit faster here and there. It's really about parallelization, right? Everything has to be parallelized as you scale data up beyond the size that can fit on a single machine, and everything's going that way. And so if you're not parallel, then you don't scale. So how would you parallelize this? Well, everything we've talked about is sort of inherently sequential, right? Because even in stochastic gradient descent, it's very, very fast because it's only processing a single data point, but each data point changes the parameters, and then those parameters are used to compute the next data point. So there's this dependency iteration to iteration. All right. So what would happen if you just did this in parallel without worrying too much about making it sequential. So the result could be nonsense, but it turns out that it's not nonsense and it could actually converge. And so what some folks have shown, a couple different groups actually more or less independently, and the paper I've cited here is the one that I'd recommend, has this approach called hog wild. These authors name their approach hog wild, which is to parallelize stochastic gradient descent, just take in each of the threads, in each of the independent processes, start trying to update the parameters using a random data point, and you can apply this to mini-batches as well. Now, you know, it's unpredictable which order these updates will happen in, and therefore it's unpredictable which values of the parameters you'll use to compute the new value, right? You may have one thread's updates but not have another thread's updates, and so on. But what they were able to show is that you still make progress on this. And so what was kind of fun about this is it came out, you know, very empirically from a student of Chris Ray's working to try to improve performance here and just trying out ideas. And so they said, look, you know, what might happen if we just remove the concurrency control in this parallel program? We just move the locks, right? So we no longer sort of worry about what order things are going in and just let everything update willy-nilly, which is why they kind of called it hog wild. And so it turned out it kind of worked, and it got, you know, a good answer, and you applied to other data sets and they got a good answer still. And so they went back and looked analytically and sort of studied whether this would actually converge in most cases, and were able to sort of prove that it would. But I think, you know, one thing I like about this is, first of all, it gives you a parallel method for stochastic gradient descent, which is nice, but it also sort of shows that, you know, the exploration and the empirical kind of trial and error approach, doing intuitively what might make sense in some of these cases, is perfectly reasonable. And then it doesn't necessarily tell you any formal guarantees about what you've done, but it might sort of give you a starting point. So how does this actually look like? Well, let's say we have two different threads that are all going to be applying this parallel stochastic gradient descent algorithm. And if we sort of say time is increasing going down the slide here, well, in the first step we update parameter theta 0 from its old values and the current, you know, the old value of theta 1 as well, and we happen to randomly pick the third instance, so x3, and we compare it with y3. And remember, we don't need this multiplication by x3 here out here because this is parameter 0, which is the slope. So there's kind of a in times 1.0 here. Okay, and then at time 2, a different thread will see these new values created that were updated at time 0 and use those to compute a new theta 0 here. And then at time 3, we're still using the original 0th value of theta 1, but we're using the second value of theta 0, and so on. And so it's unpredictable. With only two threads, you could sort of see maybe a pattern here if they're interleaved exactly the way I've seen, although there's no guarantee that they would be interleaved in this way. But you can see that it's sort of unpredictable, but the point is, as long as it's generally making progress, it's perhaps the exact ordering, the exact interleaving maybe doesn't matter. They're all getting updated, they're all sort of an estimate of the gradient, and they're all getting closer to that minimum.